In this video, we will look at voltage regulation. In terms of terminology for voltage regulators, we have line regulation, which is how much the output voltage varies when you have a varying input voltage into the regulator. Load regulation is when the load you are driving varies, how much ripple is there in the output voltage from the regulator. The output ripple is when you have ideal circumstances, a steady load and a steady input voltage. What is the ripple in output voltage? The power supply rejection ratio is a ratio of the input ripple compared to the output ripple. When you use regulators, the input voltage has to be higher than the output voltage. This is known as a certain dropout voltage, and the input voltage has to be above a certain value for the output voltage to maintain its output at a specified value. And then the efficiency is defined by the output power from a regulator as compared to the input power. The more efficient it is, the better in terms of the energy transfer, and also the less heat is generated. So an inefficient regulator will generate a lot of heat. Linear voltage regulators come as 3-pin devices. You've got an input, an output, and a ground. To improve the performance of these regulators, you put an input capacitance and an output capacitance. So this just helps to smooth the signal and lower the ripple in the output. They're not very good in terms of efficiency, so you need good heat dissipation for these devices. In terms of how they work, this would be a typical circuit for a linear voltage regulator. What you have is an input voltage. So we will say that is 10 volts, for example. We've got a potential divider circuit here going to ground. So we've got 0 volts here. So if these were two resistors, here and here, then the reference point would be a fraction of that voltage drop. However, that voltage would vary if this voltage varies. So instead of using a resistor for this low component, what we do is we use a Zener diode. And if you think back to our lecture on Monday, a Zener diode is used in reverse bias configuration, and it is used that way because there's a very specific voltage drop across this device. Okay, so what we might get is something like 1.2 volts at this point. So if this is 10 volts, you've got a resistor in there, this is going to be 1.2 volts. If this rises up to 11 volts, you're going to get the same voltage drop across here at 1.2 volts. So it doesn't matter what this value is doing, this is going to stay at a very precise voltage. In terms of the output, say we want an output of 5 volts here. Then if we want an output of 5 volts, this is ground here. So we want a resistor ratio here to give us 1.2 volts at this point. What we'll find is this isn't exactly 5 volts. This might creep up a bit. So this might creep up slightly to say 5.1 volts. In which case, this will go slightly higher. If this goes slightly higher, then this is going to be at a slightly higher voltage than our reference here of 1.2 volts. So this is going to be a negative output, and this is going to switch off this transistor. So this transistor is now switched off, so no current's allowed to flow through here. So this output voltage, you're losing current through the load in this direction, so this voltage is going to drop. So now this voltage might drop and it might say go down to 4.9 volts. This drops to 4.9 volts. This now is less than 1.2 volts at this point. This is still 1.2 volts. Therefore, this is going to switch to an output, positive output, which will turn this transistor on. So current will flow through here. And therefore, this will start going back up again. So what you can see is this voltage will slowly go up, up and down and up and down. As it goes up, the transistor will switch off, so it'll start going down, and then when it goes down too low, the op amp, the comparator, will go high, switch the transistor back on, and then the voltage will start going back up again. So this is quite a small ripple. So this will be less than millivolts ripple, so it's very small because the gain of the comparator is so high. And because this voltage reference point here is stable. So it doesn't matter what this input voltage is doing. So this can fluctuate quite widely, high and low. You'll just get a small ripple on the output side. And that's how linear voltage regulators work. The speed that this ripple is occurring at is typically about 100 kilohertz. So this ripple effect is very fast. What you can do as well is in these resistors, you can make one of these variable. So you can put a potentiometer on there. And what that does is you can effectively tune this value here. So you tune in the output. So you can make this output. So tune it to what value you want. So you can get tunable voltage regulators. Switch mode regulators use inductors and capacitors to store energy. You've got a large variation of output from these. You can have an output that is less than the input voltage. You can have an output that is greater than the input voltage. And you can also have an output which is reverse polarity. So if you've got a plus supply going in, you can make it a negative supply coming out. They're a lot more efficient than linear regulators, and you can get a lot higher currents. Because they're more efficient, they don't generate as much heat, and therefore higher levels of current are possible. The downside is there's a significant ripple. So the undulation on the output is a lot greater than the linear voltage regulators. There's two types. There's charge pumps, and these are for low current applications, and these use capacitors as the operational principle. And for large currents, these use inductors, and you've got a choice of buck boost, and flyback. So what we'll do is we'll have a look at each of these and see the operational principle. This is a schematic of a buck regulator. You have your input voltage, you have a switch, so this is an electronic switch controlled by a signal, and then you have components, the main part being this inductor here. So if we close the switch, we have no current flows through the diode as it is in reverse bias, and the capacitor is charging. So if we close this switch here, so current is flowing through here. We cannot get current in this direction because we've got this diode. All the current has to flow through here. It flows around like this. So it's flowing through the load. It's also charging this capacitor up here. So when the switch is closed, capacitor is getting charged, current is flowing through the load. The potential across the inductor is VI, or V input minus V output. So you can see when the switch is closed, we have V in there, V out on this side. So the potential difference across there is V in minus V out. Now with the potential difference across an inductor, what you'll get is a buildup of charge. So the defining equation for an inductor, V equals L di by dt. So with a voltage or potential difference across the inductor, the current is going to build up. So what we can do is integrate this over time, and if there's a voltage applied for a given time, work out how much current has built up over that time. So if we rearrange this in this format and integrate, what we find that between time 0 and time t, there is this much current builds up in that inductor. When the switch is open, current still flows through the inductor but is decreasing. Okay, so what we've done is we've now closed this switch, so we're not getting any current through that way. Now there's current build up in here, and again, if you think back to driving motors, you kind of instantly stop a current going through an inductor, and the current has to slowly die away. So we're getting current still through here, so the current is still being forced through this route, but this switch is now open, so we kind of go through that route, so the current goes around this way. So we've got earth at this point, so the potential across the inductor now is V out 0 on this side and V out on this side, with current flowing in here. So the potential across the inductor is ground 0 minus V out. So again, what we can do is work out the change in current over a certain period of time, which is from time t to time we'll call it capital T. So we integrate that to get that value. So while this current is slowly decreasing, what is happening is that this capacitor is also slowly discharging. If we consider the energy stored in the inductor, this is given by this equation. So the energy in the inductor is that. So over the first time cycle, the energy change is this, or the current is this, which corresponds to a certain energy. And then the current change in the next part of the cycle is this, which corresponds to a certain change in energy. And over one complete cycle, the energy change has to be equal to 0. You cannot be getting a buildup of energy in this. Okay, so as one cycle is close the switch, open the switch, over that closing and opening process, the total change in energy in the inductor has to be equal to 0, and therefore the sum of that current and that current has to total 0. So the sum of the change of currents has to ultimately be equal to 0. Otherwise, you get a buildup of energy, which is unrealistic. So this gives us our equation. And what we can do is replace our variable t, which is the time the switch was closed for, with a value of d, so it's dt, where t is the time that it takes the switch to close and then open, so it's one cycle, the time for one cycle, and d is the duty cycle, so it's a fraction of the time in that cycle that the switch was closed. So if we replace t with dt in this equation here and here, and rearrange, what we get is the output voltage is the duty cycle times the input voltage. So duty cycle is going to be between 0 and 1, and therefore the output is going to be less than the input voltage. So it's going to step down the voltage. For the boost regulator, we have our inductor here and our switch here. So when the switch is closed, current flows through the inductor only. So we've got the switch closed here. So we've got our input voltage here, we've got current flowing through here, down this path, and around in that loop there. So this is the easiest path for the current to flow, because this will be a resistance on this side, so the current prefers to flow through this path. This capacitor, will say it's charged, so this capacitor will discharge. It cannot go this way through the diode, so it has to go this way. So the capacitor is discharging through the load. So when the switch is closed, the current driving the load is the charge stored on the capacitor. So we can say when the switch is closed, the potential across the inductor here is V in at this side, and this is now connected to ground here. So this is 0. So the potential across the inductor is VI, and therefore the buildup of current, similar to the previous case, we integrate, or for the time when the switch is closed, 0 and t, and we get this term out. When the switch is open, current flows through the inductor and load. So if you have this switch open now, so current cannot flow this way, the current is going to flow in this direction. So this is going to pass current through the load and is also going to charge the capacitor. So this capacitor is getting charged now. The potential across the inductor in this scenario is VI minus V out. So you can see V in here, and then it's V out here. So assuming no potential drop across here, that's going to be V out. So the potential across this is V in minus V out. And again, we can work out the change in current of time t to capital T, giving us this equation. Again, we can say the total change in current during the cycle is 0. So we cannot, each cycle, we cannot keep continually getting an increase in current, which would increase the energy. The total current change has to be 0. So we can have both of these terms equal to 0. Replace the t's with dt again, as so represented in terms of the duty cycle. And we get this expression out for the output. So in this case, it's a slightly different transfer function, and because d is between 0 and 1, this denominator term is going to be less than 1, and therefore the output is going to be larger than the input. So it is stepping up the voltage in this case. This is the buck boost regulator. So again, we've got our switch, our inductor. In terms of analysing this one, it's easier if you know the answer to start with, and then it's easier to visualise. So I'm going to tell you that the output is negative. Okay, so it's a negative voltage on the output supply. So just think about that while we're analysing this circuit. So what we have is we close the switch. So current is flowing through here. You cannot get any current flowing through that way because the diode will be in reverse bias. So you get current flowing around there. The capacitor will discharge, and the capacitor, if this is ground here, and this is going to be a negative output, which we'll see at the end, then the capacitor is going to discharge like that through the load. So we get the capacitor discharging through the load. The potential across the inductor is VI. So this is ground here. So this is 0 volts. This is our input voltage at this point. So this is V in. So the potential drop across this inductor is V in. So same procedure, given that we've got potential across that inductor, we can work out the change in current. So perform the integration and we get a change in current over time t of VI over L times T. When the switch is open, so now when we switch it open, we can't get any current flowing through there. We've got current flowing through here in this direction, so we cannot immediately switch off that current, so the current will slowly decrease, and that'll be the current path. So what it's doing is driving current through the load and also charging the capacitor back up during this time. And if you can see, this is at 0. The potential at this point here, ignoring any voltage drop across the diode, so assuming there's no voltage drop across here, the potential at this point is V out. So when the switch is open, we're going to get a potential across the inductor of V out. Again, we can work out the change in current, which equates to this. We let these two terms sum to 0, so we don't get any change in current over the cycle. And we replace our t's, t and t, with dt. And we get for the transfer function this term. So the output is minus d over 1 minus d times V input. So depending on the value of d, we can make the output voltage larger or smaller than the input voltage, but there is a negative sign on it. So if the input voltage is positive, the output voltage is going to be negative. The flyback regulator is essentially exactly the same as the buck boost regulator, except rather than having an inductor, it's got a pair of coupled inductors. So you can think of this like a transformer where the current in one inductor is then coupled to produce a current in the other conductor, just like a transformer. So there are advantages to this. First of all, you can change the polarity of the output. So you can either have this, you can have V out to be the same polarity. So you can have this as positive, or you can have it as negative. And that is just a question of the sense of these coils with respect to one another. Okay, so if you turn these coils in the opposite direction, then you would change the polarity of the output. The second advantage is you can control the output compared to the input with the ratio of the number of coils on the primary and the secondary coils. So you've got a lot more control on the output voltage simply by changing the number of coils in your inductor. The third advantage is if we extend this down, so you can imagine you've got a primary coil and you've got multiple secondary coils. So potentially you could have different circuits or different regulator circuits coming off these different coils, so you can have multiple output voltages coming out of this regulator. The only problem with that is this PWM controller, it switches with respect to a reading from this output voltage, so it regulates the output voltage, and you're only able to regulate one output voltage. So you can have multiple output voltages, but you'll only be able to regulate one of them. So to compare our linear voltage regulators and our switching voltage regulators, the linear voltage regulators have got a lot better quality output. So they've got a lot less ripple associated with them compared to the switching mode type. However, the switching mode type is a lot more efficient and allows for a lot higher current to be produced. These regulators would typically be used in power supplies. The linear voltage regulators are used in linear power supplies, and if you get a power supply from the electronics workshop, it will typically be a linear power supply where you get a stable low noise output, so you get a very good voltage output from these, constant level. However, they are large and heavy and expensive to buy. On the other hand, switching power supplies, these are a lot cheaper, low cost, light, and have a higher capacity. The downside being they have a noisier output voltage. And these switching power supplies would be the type of power supplies you find in your typical consumer electronics. So for example, your PC, your DVD player, your washing machine, etc. In terms of making a power supply, so this is something you should not do. It's very specialized and you need to be careful doing this because you're handling high voltages. But in terms of the theory behind it, you've got mains power here and you want to convert this to some output. So this might be a 5-volt output you wish to use. So the way it works is you have your mains coming in at 230 volts. Yeah, and this will be in the UK, it is 230 volts and 50 hertz. So there's your signal. This then passes through a diode bridge rectifier. So if we just remove that capacitor for now, at this point in the circuit, you'll get a rectified signal. So instead of going plus or minus 230, it would just be 0 to plus 230 along here. If we put the capacitor in, we smooth it out a little bit, so it's still quite a rough signal but smoother, and then our output here is our regulated 5-volt supply, which is what we're after. Because this is high voltage, this has the potential of electrocuting somebody. This is our user side, which is 5 volts, which should be safe, but what we need to ensure is there's no way that this high voltage, this 230, can somehow get across to this side. The problem we have is this output voltage needs to be monitored by this PWM control of the switch to regulate the output. So we need a signal going from here to here, but we're not allowed to have a hardwire connection because we don't want to risk electrocuting somebody with this high voltage. So what we have in the circuit at this point is some kind of isolation, so we can send the signal through here, but it's not electrically connected. And this would be typically something like an LED, say for example, and a photodiode. So you can transmit the signal across this point, but there's no actual hardwire connection, and therefore there's no chance of electrocuting the user. So that ends our discussion on voltage regulation. In the next video, we will look at batteries.